We're going to continue on in chapter P2 with more review, looking this time at exponents and then scientific notation. The zero exponent property says that any non-zero base raised to the zero power equals 1. In our example 1, all three of these values have a non-zero base, so all three of them are equal to 1. The negative exponent property says that any non-zero base raised to a negative power is equal to the reciprocal of the base raised to the positive exponent. So what that looks like here in example 2 is, remember, 7 is actually 7 over 1, so the reciprocal of that is 1 over 7, and then instead of a negative 2, we have a positive 2 for the exponent. So we simplify that to 1 over 49. In B, 3/2, the reciprocal is 2/3, and then again the negative goes away, so we have a positive 4 for our exponent. When we simplify that, we get 16 over 81. Now we're going to look at some properties of exponents. These are going to apply for all non-zero real numbers, a and b, and integers, m and n. The product rule says that if we're going to multiply powers with the same base, such as a to the m times a to the n, that will equal a to the m plus n. In example 3, these all have the same base, so this is going to equal 4 to some power. We're going to add them. So 2 plus 3 is 5, and then y is not a like term, so it's going to stay by itself. In B, we're going to have to distribute this into the parentheses, and so we get x to the negative third times x to the fifth plus x to the negative third times x to the third. And now we're going to apply the product rule to each of these terms. So x to the negative 3 plus 5 is a positive 2. And then negative 3 plus 3 is 0. And now this term, we can use our zero exponent property from earlier, so that actually equals x squared plus 1. The quotient rule is for when we divide powers with the same base. In this case, a to the m divided by a to the n equals a to the m minus n. In example 4, we have numbers and then 3 different variables, so we'll treat each of those separately in simplifying this fraction. So the negative sign is going to stay there. 15 and 40 are both divisible by 5, so we can simplify that to 3 and 8. And now we're going to look at each of our variables. So x is raised to the 7th and then minus 3, so we are left with x to the 4th in the top. Next, we're going to look at y. We have 2 in the top and 8 in the bottom. 2 minus 8 is negative 6, so we are left with a y to the positive 6 in the bottom of our expression. And then z to the 4th and z to the 4th in the bottom, so those are going to cancel, so that is our final answer. Next up is the power of a product. So if we have a times b raised to the m, that is a to the m times b to the m. So essentially we've distributed that exponent into both of those. In example 5a, we're going to do the same thing. So we're going to have negative 5 cubed times x cubed and y cubed and z cubed. And negative 5 raised to the 3rd power is going to be negative 125, and then these ones just stay the same. For example 5b, I want to point out that in this case, if I have x plus y squared, that does not equal x squared plus y squared. What it really equals is x plus y times x plus y, which usually then you would FOIL. So with example 5b, we're going to have to look at what's inside the parentheses first. We're going to use our order of operations. So 2 squared is 4, 2 cubed is 8, and then all of that is squared. So 12 squared equals 144. The next property is the power of a quotient. So if we have a fraction that is now having a power applied to it, we are going to do the same thing and we're going to distribute. So a over b to the m is a to the m over b to the m. In example 6a, you want to make sure that you distribute that to all parts of what's inside the parentheses. So that's going to give us 3 cubed, or 27, x cubed over y cubed. In example 6b, we're actually undoing this property because all three of those numbers, 4, 2, and 12, all have the same exponent. So in this case, we can set this equal to 4 over 2 times 12, and then put the exponent on the outside of our parentheses. Now we have something we can simplify. So we're going to do that. 4 over 24, still raised to the x, equals 1 over 6 raised to the x. 1 times itself any number of times is still 1, so that's going to equal 1 over 6 to the x. Our final exponent property is the power of a power. So if I have something that is already raised to a power and then I apply another power to it, in this case it's going to be a to the m, all of that to the power of n is a to the m times n. In example 7, again, be careful that you do this to everything inside those parentheses. So x cubed to the 6th is x to the 3 times 6, which is 18. And then y to the 4 times 6 is 24. And then all over z, and then 2 times 6 is 12. Now we're going to look at using these properties to simplify some expressions. In 8a, we're going to take 3 times negative 4, which is negative 12, and then we're going to apply the product rule for exponents. So it's the same base, z, and then 7 plus 2 is 9. For b, we're going to have to distribute this in and then do some simplification. So y is only here once, and when I put that 3 in there, it's y cubed. And then we're going to have z to the 3 times 3 is 9, over z to the 5 times 3 is 15. So that y is going to stay the same. And now I have the quotient rule. 9 minus 15 is negative 6. All right? But since I don't want a negative exponent, I'm going to put it in the bottom with a positive. In c, this exponent is 0, so automatically this expression equals 1. In d, we're going to be looking at our negative exponent property. And so, remember 5 is actually 5 over 1, so this is 1 over 5 cubed, which is 1 over 125. E is a little more complicated, so we're going to take this bit by bit. So first, we're going to look at the 5 to the negative 2. Because I have a negative exponent, and I don't see 5 anywhere else in this expression, to get rid of that, I'm going to put the 5 in the top with the positive 2. Now, let's look at something else. This 2 doesn't have any exponent on it, so we're just going to leave it in the bottom for now. The negative 2 has a negative exponent, so to get rid of the negative here, we're going to want to move this to the bottom, but what's inside the parentheses stays negative, only the exponent changes. And now x to the negative 6, all right, I want to move that to the bottom to get rid of the negative exponent to make that positive. And then the y to the negative 4th, I want to move that to the top to get rid of the negative. Now, all I'm left doing is simplifying my numbers. All right, I know I am going to have y to the 4th over x to the 6th in my answer. And then the top is 5 squared, which is 25. And negative 2 squared is 4 times another 2 is 8. For f, we have a negative exponent, so we're going to take the reciprocal of what's inside, so negative 3 halves, and then this becomes a positive 3. And now we have to distribute that in. The negative can go with either the top or the bottom. I like to leave it with the top, so that's negative 3 cubed, which is 27. Over 2 cubed, which is 8, and that's still an equal sign. Next, we're going to look at some critical thinking problems. So for each of these, we're going to decide which one of these statements is correct. In A, right, we're looking at a product, and then they have power. So this is going to be the product rule, which means that I add the exponents, giving us this choice. All right, 3 plus 4 is 7. For B, this is again the product rule. So when I do that, my base stays the same. It does not multiply the base. So this one, 3 squared times 3 to the 4th equals 3 to the 6th is my correct answer. For C, this is a quotient rule, in which case the bases all stay the same, and then 16 minus 4 is 5 to the 12th, so this is my answer. For D, remember, we have to distribute that exponent to everything inside the parentheses, so it is not just 4 times a cubed, it is also 4 cubed, which is 64, giving us this as our correct answer. 2 more before we move on to scientific notation. In E, this is going to be a negative exponent property, which, while it does get rid of the negative sign in the exponent, does not change the value of the overall expression. Therefore, b to the negative n equals just 1 over b to the positive n. F is similar to example 5b. When I have something added inside my parentheses here with an exponent, I cannot distribute that inside like I would with multiplication. So here I have to treat a and b as a singular quantity. So a plus b must be in the bottom of my fraction, giving us this answer choice. Scientific notation is what we use to express very big or very small numbers. You've probably seen this in chemistry and/or physics class. So we write this in the form of some number times a power of 10, where a, that number out front, is going to be a single-digit number between 1 and 10, perhaps with a decimal following it, and then n, that power of 10, is going to be an integer. So we're not going to do example 10. We're going to skip right down to converting scientific to decimal notation. So for example 11, all right, to move a number from scientific notation to decimal notation, if there's a positive exponent, we're going to move our decimal to the right. And if we have a negative exponent, we're going to move our decimal to the left. And that should say decimal. For A, all right, this is a positive exponent, so we're going to move to the right, all right, and we're going to move 9 spaces. So the negative 2.6 stays the same, but then I go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I fill in each of those with a 0, and then the decimal goes away. So I am left with a 2, a 6, and then 8 zeros, and this is usually helpful if you put the commas in every third, like that. On B, we have a negative exponent, so we're going to move our decimal to the left this time. So if I have 3.017, and then I'm going to move this decimal to the left 6 places, so 1, 2, 3, 4, 5, 6, and again, I put a 0 in each of these, and that's where it's going to go. So I can rewrite that as 5 zeros and then a 3, 0, 1, 7. To go the other direction and convert from decimal notation to scientific, all right, the first thing you're going to do is determine the single number between 1 and 10 that you're going to use, and then you're going to figure out how many places you're going to move the decimal to get there. So essentially this is the other direction from example 11. So what you really need to know is that a positive exponent is a big number, so like trillions in the example given above. A negative exponent is going to be a small number, and that's for something that's much, much less than 1. So in example 12, our number is going to be 5.21, and then our decimal started here, so we moved 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So this is a big number. So this is going to be a positive exponent, and we moved it 9, so it's 5.21 times 10 to the 9th. For B, our first number that we see here is a 6, and then 0.893. The negative out front just stays. Now, to figure out what my n value is going to be, because it's going to be times 10 to the something, I have to figure out how many places I moved that decimal. So it was 1, 2, 3, 4, 5, 6, 7, 8. And it's a very small number. It's much less than 1, so it's going to be a negative 8. Finally, we're going to look at some computations using scientific notation. Now, in example 13, since this is all multiplied, and it doesn't matter what order I multiply, it might be easier to think of this as 7.1 times 5 times 10 to the 5th times 10 to the negative 7th. And now you can see that these two together, 7.1 times 5 is 35.5. And now we're using our exponent rule on this portion. So 5 plus negative 7 is 10 to the negative 2 there. But I'm not quite done because it's not in scientific notation. This number needs to be between 1 and 10, and right now it's not. So to do that, I make that 3.55, and since I made this number smaller, my exponent's going to become a larger number. Now, I'm going to move it one place because that's how many I moved it, but one number larger than negative 2 is actually negative 1. So that is my answer. In B, 1.2 divided by 3 is 0.4, and then we're going to use our exponent rule for 10 to the 6th divided by 10 to the negative 3rd. So this is a quotient, so I'm going to subtract my exponents. So 6 minus negative 3 is actually a positive 9. Again, we're not quite done. It's not in scientific notation. So in this case, I need to move this decimal place over to get 4, and then it's still going to be times the power of 10. Since I made this number bigger, I need to make my exponent smaller. So 1 less than 9 is 8, and that's my final answer. Our final problem is a word problem. So here, we're going to look at the number 2.6 trillion, and then we're going to look at a population of 312 million. So we want the cost divided by how many people. So how much each citizen would have to pay for the war. So here is where you need to be careful. A trillion is 10 to the 12th. A million is 10 to the 6th. So we can't just divide the numbers, we have to use that scientific notation. So if I was going to write this as the cost, which is 2.6 times 10 to the 12th, divided by the number of individuals, 312 times 10 to the 6th. All right. Now, to do 2.6 divided by 312, you can put that in the calculator, and you get something like 0.00833. And then you have your quotient rule for 10 to the 12th divided by 10 to the 6th, which is 10 to the 6th. 12 minus 6 is 6. But, again, I'm not done. I need to put this into a dollar amount, okay, in the nearest $100. So what I'm really doing is actually converting this back into a decimal form and then rounding to the nearest 100. So if I move this 6 over, so in order to get rid of the 6, I'm going to move this 1, 2, 3, 4, 5, 6. All right, so I end up with 8, 3, 3, and remember I have to fill in that gap with a 0, and then I have some dollars, all right, but then it does want to the nearest $100, so rounded, that is $8,300.